radioactivity. It's a very easy and scoring subject article for board examinations as well as for competitive examinations. And you will find that we have done things which are similar to radioactivity in capacitors and inductors. Let's first understand what radioactivity is. If we have a highly unstable nucleus, then it emits alpha rays, that is alpha particles, beta rays, that is electrons, and gamma rays, which is electromagnetic radiation. And with the help of this, it makes itself stable. Now, in a given sample, we have no idea which nuclide is going to disintegrate and will give us alpha, beta, or gamma. And therefore, we use something called probability. You don't have to worry about probability and all. So, the thing is, if we have a large sample in which there are n number of active nuclides present. What is n? Number of active nuclides present in the sample at time t. This n is the number at time t. Then at time t plus dt, we found that number of active nuclides is n plus dn. Now, we are discussing radioactivity. That means disintegration is happening. Number of active nuclides, this number is continuously decreasing, but still I am using what? Plus, because this is maths. For x, something is y, and therefore for x plus dx, it should be written as y plus dy. But you know that this dn therefore should be negative. Then only disintegration will take place. Now, law of radioactivity, it says that dn upon n, dn upon n, this thing is proportional to dt. What is it? dn, number of nuclides which are disintegrating, this number divided by total number of active nuclides present at any time is proportional to time interval in which this whole disintegration took place, which is what? dt. Now, those who are from maths, they know that dn upon n is called probability of disintegration. dn, number of active nuclides which are now not active, disintegrated nuclides. Active nuclides present, that's your probability of disintegration, and this probability is proportional to time in which this disintegration took place. Now, this dn by dt, once you say is proportional to dt, when you remove this proportional sign, we use a constant, and when we write the constant, we write this constant as lambda multiplied by dt, and now we'll be using a negative sign also. What is negative sign? This negative sign is telling you that this dn is negative. That means number of active nuclides, that number is continuously decreasing. This format is called law of radioactivity. dn upon n equals to minus of lambda dt. This lambda is called decay constant. Lambda is called decay constant. And you will understand this decay constant in terms of something which you are familiar with, that is called half-life after some time. Now, write down a few things. N is number of active nuclides present. N is number of active nuclides present at time t. At time t. In time interval dt, if dn nuclides disintegrate, in time interval dt, if dn nuclides disintegrate, then it is found that probability of disintegration is proportional to time in which disintegration took place. Time in which disintegration took place. Now, if you write this thing as probability, then you can do this also. You can write it like this, because without mod, this probability will look negative, because dn is what? Negative. Now the whole thing is what? Positive. And this probability of disintegration is proportional to dt. Now when you remove the proportionality sign, you will simply write dn upon n as minus of lambda dt. Lambda, write on the statement. Lambda is called decay constant. Lambda is called decay constant, and it is a constant for a given type of nuclide. And it is a constant for a given type of nuclide. For different nuclides, lambda will be different. For different nuclides, lambda will be different. For example, for uranium, lambda will be different. For plutonium, lambda will be different. But for a given nuclide, lambda remains constant even if temperature or pressure is changed. Even if temperature or pressure is changed. I mean, if you change the temperature or pressure, if you increase pressure or decrease pressure, this lambda will not change. It will remain a constant. Even if you put this material in a very high temperature zone, even then your lambda, it remains what? Constant. It's a universal constant for a given nuclide. Remember it like this. It's a universal constant for a given nuclide. That means for uranium, value of lambda at Earth, Jupiter, in some other galaxy, at some different temperature, at some different pressure, that will remain same. Now, once we observe this thing that dn upon n is proportional to dt, we found this dn upon n as minus of lambda dt, then we can develop n as a function of time. Our aim is to find number of active nuclides at any time t. Write down the question. If initially number of nucleides, if initially number of nucleides are n naught, if initially number of nucleides are n naught, then find out find out number of active nucleides, number of active nucleides at time t. Now, I said initially, that means at t equals to 0, number of active nucleides, that number is given as what? N naught. Our aim is to develop n as a function of time. And at this stage, pause the video, give it 2-3 minutes, and I hope you can develop n as a function of time. And once you develop that, you will find that it resembles to something which we have already done in capacitors and inductors. And then come back and see the solution. So, law of radioactivity says that dN upon dt is minus of lambda n. You will also find law of radioactivity written in this form. dN upon dt is what? Minus of lambda n. dN upon dt is what? Minus of lambda times n. This dN upon dt, although we are not interested right now, but you can remember that this dN upon dt is called A. This A is what? Activity. A stands for activity of the radioactive sample. dN upon dt, rate of disintegration of active nucleides at time t, is called activity. Now, if you have been given something in this form, which is dy upon dx is equal to minus of some constant times y, then how do you integrate a function like this? For integrating something like this, you will take same type of variable to the same side, that gives you dN upon n as minus of lambda dt, which is this original version. dN upon n is what? Minus of lambda dt. Now when you integrate this thing, this is dx upon x, and integration of dx upon x is what? Log x, and therefore it becomes log of n, which is minus of lambda. Integration of dt is what? T plus constant of integration, dx upon x log n minus of lambda t plus c. How do you find this constant of integration? We have been given this information that at t0 n is what? N naught. If you put this information, then it becomes ln n naught t is 0 plus c. That's how you get constant of integration, which makes it ln n minus of lambda t plus c, which is ln of n naught. Now, ln of a minus ln of b, log a minus log b, that is log a upon b, it becomes log n divided by n naught, which is minus of lambda t. Now, what is ln? ln means log with base e. N upon n naught is coming minus of lambda t. Now, how do you remove log? When you remove log, it becomes this n upon n naught e to the power minus of lambda t. E to the power minus lambda t is n upon n naught. This gives you n as n naught times e to the power minus lambda t, number of active nucleides as a function of time. You can verify this thing for t equals to 0. If you put t equals to 0, it becomes e to the power 0, which is what? 1. And that gives you n as what? N naught. Now, I told you that this is something which you have already done in capacitors. If you remember charging and discharging of capacitors. So, disintegration, radioactive disintegration is equivalent to what? If you look here, is equivalent to what? Discharging of a capacitor. If you remember, during discharging of a capacitor, we wrote Q as Q naught e to the power minus t upon tau. This was charge as a function of time on a capacitor when you remove the battery and discharging takes place. This and this, look, they both are what? Equivalent. And that can give us a hint or kind of a trick for solving something, certain questions which we did in capacitors, and similar type of questions you can expect in radioactivity. And same thing, something which you develop in radioactivity can be used in capacitors also. What is that? You will see later. Now, this is n as a function of time. Note down this much and then plot a graph of n versus time. Note down this much. Try to draw a graph of n with t. Note down this. Now look, how do you plot a graph? Vertical axis is n. Horizontal axis is what? T. Now this graph cannot go up because we are discussing what? Disintegration. And therefore it should come down. Graph cannot be a straight line because this is not a format of y equals to mx type. And therefore remember, graph will be like this. And if you remember discharging of capacitor or decay of current in an inductor, then graph was like this only. Number of active nucleides, initially that number is n naught. And as time increases, number of active nucleides, this number decreases, and when you reach infinity, then t becomes infinite. All the nucleides, they have now disintegrated. That's how you plot the graph. In this graph, we are interested in few special points. And these special points are, the first one is half-life. Write down the heading, half-life of a radioactive sample. This half-life is represented by T half. We are interested in finding T half. You have the formula. Use the formula and find out T half in terms of lambda. Pause the video. It should take just 2 minutes to develop T half in terms of lambda using this formula. And then come back and see the solution. So what is half-life? Half-life means if at t equals to 0, n is n naught. If number of active nucleides at T0, this number is what, n naught, then when your T becomes T half, then this n should be n naught by 2. This is the theme. In T half time, n naught by 2 nucleides, they have disintegrated. That means if in this formula you put n as n naught by 2, then this T should be T half. That's all. Now it's only simplification of this format. For that, look here. N naught by 2, n naught cancel. Take log. After cancelling n naught, take the log, which is ln of 1 by 2, ln of e to the power minus lambda into t half. Now, log 1 by 2, this is minus of log 2, and this is only minus of lambda t half. For bio people, look here. Log 1 by 2, you can write it as log 1 minus log 2. Log 1 is 0, that gives you minus of log 2. Or log 1 by 2 is log of 2 to the power minus 1, and you can move this power as coefficient, that gives you minus of log 2. Then for the next part, there is a property of log. If you wish, you can see a lecture on log. It's present on the YouTube channel, and you will find all these log related formulas in that. There is a property of log which says that log a to the power b is b. Log a to the power b on base a is b. It's nothing special. Those from maths, they know that. They are all elementary things. This b moves as a coefficient. Once you move this b as a coefficient, you are left with log a, which is 1. Why is it 1? If you are interested, go and see that lecture. But remember this property, that log a to the power b on base a is what? B. What is log? Ln. Log base e. So this ln is basically log of base e, and on that base you've got e to the power minus lambda t half, which gives you this. Cancel negative signs, and you got your t half as log 2 divided by lambda. This is the half-life of a radioactive sample in terms of its decay constant, which also says this: for each and every radioactive nuclide, for each and every radioactive nuclide, product of half-life and decay constant is always a constant. What is that constant? Log 2. You can remember it in this form also. For different radioactive nuclides, T half, that is different, lambda, that is different. All of them, product of T half and decay constant is always what? Log 2. When you say log 2, remember base is what? E. In this graph, if I say that this is the point which corresponds to T half, right at this place, if you say this is your T half, and at this T half position, N will be now N naught by 2. At this point, N naught becomes what? N naught by 2. In what time? T half. So, if I ask you a question, I told you that they can ask questions which you normally do in radioactivity, and you can expect those questions in discharging of a capacitor in any competitive examination. So if the question is this, what is the half-life? What is the half-life of charge on a capacitor once battery is removed? What is half-life in terms of R, resistance of the circuit, C, capacitance of the circuit? Write down the question. What is half-life? What is half-life of charge on a capacitor in discharging mode? In discharging mode. So, what is half-life? If you go for half-life, look here. You will say that T half is ln 2 divided by lambda. But what is lambda? Coefficient of T. What is coefficient of T? Coefficient of T is what? 1 upon lambda. 1 upon tau. 1 upon tau. Now what was tau during discharging of capacitor? This tau was R multiplied by C, and therefore T half is coming R C log 2. We have calculated half-life of charge in discharging mode by using this similar concept. Note down this much. Now we can also represent N in slightly different form. Look at that. This N is N naught e to the power minus lambda t. What is lambda? Lambda is log 2 divided by T half. Log 2 divided by T half. That's your lambda multiplied by T. This is N naught e to the power minus of T divided by T half into log base E 2. You can write it like this. T multiplied by T half, and then ln2, this is log 2 base E. This is N naught e to the power, now look at this part, log of base E 2 to the power t divided by t half. What we have done, we have moved this coefficient minus t upon t half as power of 2. You can move this power as the coefficient, or you can transfer coefficient as power. Now once you do this, again you have a property of log, and this property of log says that a log base a b is equal to b. If this is a, this is a, this is b, then forget about log and your value is simply what? B. In this case, you can see that this is E, and therefore you can forget about log. And once you forget about log, it gives you this format. N is coming and not E gone, log gone, 2 to the power minus t upon t half. 2 to the power minus t upon t half. It's coming from this a log. These things are gone and you're simply left with what? B. It's a simple property. You can see this in that lecture which I've told you about. Now, once you write n as n naught 2 to the power minus t upon t half, you can give it the final version. Final format is this: n equals to n naught 2 to the power t upon t half, which is n equals to n naught divided by 2 to the power n, small n. What is small n? Small n is coming is equal to what? T upon t half. This n represents what? This n represents number of half-lives. Number of half-lives present in time t. Suppose you have got half-life as 2 seconds. So if half-life is 2 seconds and t is what? 8. In 8 seconds, how many 2's are present? That's what the thing is. That's what this n is. So in 8 seconds, how many 2's are present? You will say 8 divided by 2. 8 divided by 2 is what? 4. That means 4 half-lives are present. This n is this n. That means after n half-lives, number of active nucleides which are present in the sample, that number is n naught divided by 2 to the power n. This is also a good format because we'll see a few questions, good questions can be found on this part only. Go down this and then we'll see those questions. Now look at the type of questions you can expect from this profile. Let's say A disintegrates itself into B. A is your parent nucleide and B is your daughter nucleide. A disintegrates into B. Question is, after three half-lives, what is the ratio of number of active nucleides of A with that of number of active nucleides of B? We need to find this. After three half-lives, find out ratio of active nucleides of A with that of B. Pause the video, go for the question and then come back and see the solution. One way of answering the question is this. A, when time is 0, when t is 0, A is present, B is not present. Only A is present, B is not present. When T is T half, that is first half-life, N becomes N naught by 2. And what happens to other N naught by 2? Those N naught by 2 nucleides, they disintegrate and become what? B. And therefore, this is N naught by 2. If initially you had 100 nucleides of A, then after first half-life, you will have 50 of A and 50 of B. When T is 2T half, after second half-life, this N naught by 2, it will become what? Half. From this to this, what is the time duration? T half. And in T half, what happens? Number of active nucleides, they become what? Half. And therefore, half of N naught by 2 is N naught divided by 4. If this is N naught by 4, remaining N naught by 4 now are present this side, and therefore this side becomes 3 N naught by 4. You can always find this side by using this simple thing. Sum of this and this should remain what? N naught. Sum of this and this should remain what? N naught. 100 after first half life, it becomes 50 and 50. Another half life, 50 becomes 25. 25 move to this side. This is 75 now, but 75 plus 25 is what? 100. Total number of active nucleides, that will remain what? Same. Provided this N naught, there is no input from this side. We'll see the type of questions for IIT advanced type of examinations. Same time, if your B does not disintegrate, if formation of A doesn't take place, that means it remains N naught only. And if B does not disintegrate into a third nucleide of type C, then this number, sum will be what? N naught. N naught. This is also N naught. Now, what is after third half-life? After third half-life, this thing will become what? N naught divided by 8. This is the number of active nucleides present at this time. From this time to this time, we have a time duration of T half, half of this, N naught by 8. And this side, it becomes what? 7 N naught divided by 8. 7 N naught divided by 8. This means sum of these two, it should be what? N naught. So the question is, after 3 half-lives, what is the ratio of Na and Nb? After 3 half-lives, A is what? N naught by 8. After 3 half-lives, A is N naught divided by 8 divided by Nb. What is Nb? 7 N naught divided by 8. 7 N naught divided by 8, which is coming 1 upon 7. Now, this Na upon Nb is for 3 half-lives when time is 3T half. We have developed this. Suppose I ask you, what is Na upon Nb after 5 half-lives? After 5 half-lives. You don't have to repeat this thing again and again. From now onwards, you can simply remember this as what? What is 7? Look. 7 is 8 minus 1. What is 8? 2 to the power 3. So you can simply remember it in this form. 2 to the power n minus 1. This is after your t is n t half. That means after n half-lives, ratio of A and B will be 1 upon 2 to the power n minus 1. If I ask you what is this ratio after 5 half-lives, 2 to the power 5, 32 minus 1, 31. That is 1 upon 31. You can expect something like this in any examination, and it's coming from this only. What is N? Na. What is N? Number of active nucleides present. And therefore you will write Na as N naught upon 2 to the power N. What is Nb? What is Nb? N naught minus, take the ratio and you will arrive at this position. Now, a trick type of question again can be asked in this form. And if I say that after time t, which is not known, t half is given as 5 seconds. T half is known 5 seconds. We need to find t, and question says that at time t, ratio of A to B is 1 by 15. The question is asked in this form that after some time A and B, their ratio is 1 upon 15. What is that time? Pause the video, answer the question, shouldn't take more than 30 seconds. Come back and see the solution. So, 1 upon 15. What is 1 upon 15? 1 upon 15 is 16 minus 1. If this is 16 minus 1, then what is this? 1 upon 2 to the power 4 minus 1. 2 to the power 4 minus 1. That means after how many half-lives? 4 half-lives. And therefore this t is 4 multiplied by t half. What is t half? 5. And therefore answer is what? 20 seconds. If they ask a question in this form, when you find things are quite easily calculated as 2 to the power n minus 1. If they ask that, suppose the question is that the ratio is coming 1 upon 31. Now what is 1 upon 31? You know that 1 upon 31 is 1 upon 32 minus 1. Now what is 32? 2 to the power 5. So these numbers, you can always calculate t by using this fast format. Note down this.